Greetings, dear viewers and listeners, and welcome to the last chapter of the second lecture on the Spintronics Advanced Materials, which is a part of the Advanced Materials course. And before I will introduce you to undoubtedly a very interesting topic, which is dilute magnetic semiconductors, I would like to introduce myself. My name is Dr. Kristina Levchenko, and I work together with Professor Andriy Chumak in the Nanomagnetism and Magnonics group in the University of Vienna. Today's lecture will be, as already mentioned, dedicated to the dilute magnetic semiconductors, but it will be rather an overview, a quick highlight not only of these materials, but rather of the magnetic semiconductors, dilute magnetic semiconductors, and some interesting phenomena and concept devices bases that are part of the Spintronics course. So let us start with a highlight how the semiconductors are important part of the today's electronics, how are the basis for modern electronics. Of course, that many kinds of semiconductors devices have been developed in line with the expansion of application fields and the progress of electronic equipment. Here you may see several types or groups of devices where the semiconductors are used. Discrete devices are single devices with a single function, like transistor or diodes. Then we have optical devices, of course, the microwave devices that operate at the microwave frequencies. As most of the titles here are not new to you, maybe the only one new term is monolith microwave, which is nothing more than, again, the integrated circuit device that operates at the frequencies 300 megahertz to 300 gigahertz, which are typical for the microwave range. And these mimics or MMICs are used for power amplification, for low noise amplification, and high frequency switching, etc. On the sensor panel, we see quite an interesting and actually a concept device. It's a sensor, organic field effect transistor, which is ultra-sensitive sensor or actuator for pressure, for the chemical and biological detection. And in the last section, we have the integrated circuits, or ICs. Of course, these are devices with multiple functional elements that are mounted on one chip that typically consist of the memory elements, microprocessors, and logic. So, and all of these devices are based on the semiconductors. So in order to understand how these devices work and how we can improve their efficiency, one may need to come back to the origins, to the physical phenomena that underlies the transport processes in the semiconductors. And of course, here, if you wanted to learn more, please come back to the earlier lectures as the energy model, which is very important, the Jordan-Sommerfeld transport model, well already given and described within this course. Here, I would rather tell you a few quick facts that we should keep in mind while working with the semiconductors. So again, the energy model, it consists of the valence band, conduction band, and the band gap which is separating them. The valence band is a band of electron orbitals that electrons can jump out of, moving to the conduction band when they are excited. So the valence band is simply put the outermost electron orbital of an atom of some specific material that electrons can actually occupy. And it is related to the valence electrons. The energy difference between the highest occupied state in the valence band and the lowest unoccupied state in the conduction band is band gap. So in the insulators, we have a large band gap, which means that we need to supply a lot of energy to excite the valence electron to the conduction band. In the semiconductors, this band gap still exists, but the magnitude of this energy which we're supposed to supply to the charge carriers is reasonable enough to be able to do it with external field applied to the material with some temperature and so on and so on. In a metal, we know that this band overlap and we always have free electrons. Thus, we have the high conducting material. Talking about semiconductor, in its pure state, semiconductor are intrinsic materials, so ideal perfect crystal with when electron in intrinsic semiconductor gets enough energy, it can go to the conduction band and leave a hole behind. And this process is called electron pair creation. For the intrinsic materials, this creation of electrons in holes, well, they are always created in pairs. Means that we always have the same concentration of electrons in holes that are equal to some intrinsic value charge carriers. And this is hidden in this first equation, where Na and Nd are nothing else than the donor acceptor and donor concentration. Intrinsic charge carrier concentration can also be calculated from the effective density of states at the conduction band edge and at the valence band edge. Again, here we have the band gap and the KBT, which are the Boltzmann constant and a temperature. The conductivity could be calculated based on the Ne and the mobility of electrons in holes. And Fermi level, of course, it will lie in the middle of the band gap in the intrinsic semiconductor. So in order to calculate it, we just deduce half of the band gap from the conduction band or add half its value to the valence band. In the extrinsic semiconductor or in the doped semiconductor, for the N-type, for example, there is a high probability to find an electron near the conduction band edge than to find a hole near the valence band edge. Thus, it means that the Fermi level is closer to the conduction band in the N-type semiconductor. If to assume that the concentration of donors is higher than the concentration of acceptors, the electron density could be calculated as this, depending on the, again, and see the effective density of states at the conduction band edge. And from this equation, which is true for both intrinsic and extrinsic semiconductors at equilibrium, the holes are deduced as dependent on the Ne square divided by the N0. For the p-type material, where the concentration of holes is way larger, as we assume the concentration of electrons, the hole density depends on the concentration of holes, and which in its turn depends on the effective density of state near the valence band edge. And the Fermi level in the p-type doped semiconductors is lying lower than the Fermi level in the intrinsic material, so in the same material without doping. Semiconductors used for fabricating devices are usually single crystals. This is because polycrystalline materials have defects due to the presence of the grain boundaries. So these states are located in the band gap and they could modify the conductivity. So we should always keep in mind that there are some defects like shallow states that are also modifying the band gap. They are lying close to the band edges and act as sources of the electrons in holes, or there could be deep states, deep defects that are located in the center of the band gap. So these deep states can act as traps for charge and carriers and further reduce the conductivity. Also, depending on the band gap model, we can divide the semiconductors into direct band gap and indirect band gap classes. So whether the bottom of the conduction band is aligned with top of the valence band, like the lowest energy state above the band gap has the same K as the highest energy state beneath the band gap. In this case, we have the direct band gap, which means that when electron is excited, there is no change in crystal momentum. This is a situation for gallium arsenide and indium arsenide. It's important for optical applications. And indirect band gap means that the closest state above and beneath the band gap, they don't have the same K value. So the lowest state of the conduction band is not aligned with the highest state of the valence band, as you may see here on this animation. Doping is the process of adding the impurities to the intrinsic semiconductor to alter its properties. So when we take the classical semiconductors like silicon and germanium, that belongs to the group 4, which means that they have 4 uncompensated or valence electrons at the outermost shell. All we need to do is to add phosphorus or arsenide or antimony in order to get an N-type material, and add gallium, aluminium, indium, and so on in order to get the P-type material. So when we pop in the pentavalent element in the lattice, we are doping the silicon with phosphorus, for example. This pentavalent element has 5 electrons, so it shares an electron with each of the 4 neighboring of the silicon atoms. Hence, 4 electrons are tied up with the silicon atoms in the lattice. This leaves an extra electron, and this excess electron is free to move and is responsible for the conduction, hence the N-type. In the opposite case, for the P-type materials, we are popping in the trivalent element, so it has 3 electrons in its valence shell, and it shares these 3 electrons with 3 neighboring silicon atoms, with a 4th silicon atom leaves unpaired, and we are having a hole, a void in the lattice, and this deficiency creates P-type material. For the gallium arsenide, it's the same case of if we want to have an N-type material, we are replacing, as it's 3,5, it's consistent, it's compound, not just a single material like silicon or germanium. So we are replacing the group 5 arsenide by cadmium or zinc if we want to have the N-type dope material or any group 2 material. And if we want to have a hole, we are supposed to dope or replace the group 3 gallium by the, for example, group 6 element like telluride. As again, it's quite an interesting compound, this gallium arsenide. We can also add silicon, which is a group 4 lying in the middle of them. This is called the amphoteric doping. So here the dopant acts as both donor and acceptor depending on the atom's position. Usually it's very hard to control, so we are considering mostly these cases. Conductivity of a material is determined by the 2 factors: the concentration of free carriers available to conduct the current and their mobility, or the freedom to move. In a semiconductor, both mobility and carrier concentration are temperature dependent. Thus, it's important to view the conductivity as a function of temperature. In the case of the extrinsic semiconductor, the dependency of the electron concentration on the temperature is not so trivial. Here on the example of the N-type doped silicon, we can distinguish 3 characteristical regions. First one being the freeze-out region, when the thermal energy is not sufficient to ionize all donors. Some are ionized, meaning that electrons are excited from the donor level to the conduction band. And here it corresponds to the range of temperatures from 0 to 200 K. Then we observe an extrinsic region. So all donors are ionized, but the thermal energy is still not sufficient enough to excite electrons across the intrinsic band gap. And in the end, we have the intrinsic or region or the thermal energy is sufficient enough to excite the electrons across the band gap and to produce an intrinsic charge carriers. So the electrons are excited from the valence band to the conduction band. One of the crucial elements of the solid-state electronics is, of course, the p-n junction. As the die, the transistor, all of these key components are based on the p-n junction phenomena. So when p-type and n-type materials are placed in contact with each other, the junction behaves differently than either of these materials alone. Specifically, current will flow radially in one direction when it's forward biased, and it will not flow in the other when it's reverse biased, creating actually the basic of signal diode. So if we have step by step a p-type and n-type material. In a p-type, we have excessive holes from the exact impurities, and in n-type, we have extra electrons. Combining these 2 materials in a junction, some of the electrons from the n region that have reached the conduction band could diffuse to the across the junction and combine with holes. And by doing this, they're filling a holes, they are creating a negative ion on the side of the p-type material, and leaving the n-type material, they are creating a positive ion. In the end, this process continues until the equilibrium state is observed. It's a depletion region with some potential barrier. And there will be no flow of further electrons unless we apply additional energy in a form of forward bias to the junction. So the voltage required to overcome the potential barrier depends on the type of semiconductor material used and obviously the temperature, as we have seen from the previous slide. By adding two electrodes to the p-n junction, we are obtaining a signal diode. So the reverse or forward bias in these devices will lead to the either increase or decrease of the effective resistance of the junction itself, and it whether allow or block the current flow through the diode. Unlike the resistor, a diode does not behave linearly with respect to applied voltage, as the diode has an exponential current voltage dependency, as seen here. So this non-trivial dependency we can divide into several regions. They will start with reverse bias, when the positive voltage is applied to the n-type material. Of course, the electrons will be attracted toward the positive electrode, so away from the junction. And the same with the holes in the p-type, they are attracted away from the junction toward the negative electron. So the net result is that the depletion layer grows wider. And we have a high impedance pass, almost like an insulator. High potential barrier is created in the junction, preventing from current flowing, of course, through this semiconductor material. However, as you may see, when we will increase voltage up to the point of the reverse breakdown of voltage, we may cause an overheat due to the Avaloq effect. And consequently, diode becomes shorted and maximum circuit current start flowing, which is indicated by the step downward in the plot. Sometimes this Avaloq effect has practical applications. For example, in voltage stabilizing circuits, when the series limiting resistors are connected with diodes to limit its reverse breakdown current to a maximum value. Thereby, we have a fixed voltage output across the whole diode, and this is the basic of the Zener diode. In a forward bias regime, the negative voltage is applied to the n-type material. It is actually the case of the scheme, and the positive voltage is applied to the p-type material. So if the external voltage becomes greater than the value of the potential barrier, if for the germanium it's 0.3, for the silicon it's 0.7 volts, the potential barriers of the depletion region opposition will be over K, and current will start to flow. This is because the negative voltage pushes electrons towards the junction, giving them this additional energy to cross, and combining with the holes being pushed in the opposite direction toward the junction by the positive voltage. In the characteristic the plot, it results in something which is called a knee regime. It's a zero current flowing up to this voltage point. And then after the knee point, after we overcame the potential barrier, high current flow through the diode will continue. As diode can conduct from this point an infinite current, it becomes effectively again a short circuit. Therefore, resistors are used in series, again with a diode to limit its current flow. Exceeding maximum forward current causes device to give or dissipate more power in the form of heat than it was designed. And obviously, it will lead to a quick failure of the device. If you're interested in more specific parameters of the diodes, those are the maximum forward current, the maximum reverse voltage, or the peak inverse voltage, total power dissipation, and maximum operating temperature. And now we're moving forward to another building block of the today electronics. These are transistor devices that also take advantage over the p-n junction phenomena. So transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. It is a semiconductor material, usually with at least 3 terminals for connection to the external circuit. So a voltage or current applied to one pair of the transistor terminals controls the current through the another pair of terminals. Because the control output power can be higher than the controlling or input power, transistor is amplifying. So we are roughly dividing the transistors into 2 types, into bipolar, field effect, and insulating gate bipolar. Bipolar transistors are current-driven devices. Field effect transistors and insulated gate bipolar transistors, or EJBT, are voltage-driven devices. BJT uses both holes and electrons. The charge carriers are like unipolar devices like FET. Bipolar transistor allows a small current injected in one of its terminal, as it was already mentioned, to control a much larger current flowing through 2 other terminals, making a device capable either of amplification or switching. In the case of a bipolar transistor, we may have a PNP or NPN configuration. So an NPN configuration, the flowing of the majority of the carriers is from the emitter to the collector, and it forms as a current flow in the transistor. Collector terminal is always connected to the positive voltage, while the emitter terminal is always connected to the negative supply. The base is responsible for controlling this on and off switching states in the transistor, depending on the voltage which is applied to it. And such type of transistor is mostly used in a circuit because the majority carriers are electrons and they have high mobilities in holes. But PNP transistors are still used. In the PNP transistors, supply voltage polarities applied to the PNP are reversed, so a small base current and a negative base voltage control much larger emitter collector current. So the PNP transistor will turn on and open up a channel between emitter and collector when you have a small current running from the emitter to base of the transistor. But we will concentrate on the field effect transistors as they are more interesting and in most of the properties could surpass the bipolar transistors. FET consists of a semiconductor channel, again with electrodes at either side. Here are referred to as drain and source. A control electrode gate is placed in a very close proximity to the channel, so the electric charge is able to control the flow of the carriers from the source to drain by controlling size and shape of the conductive channel. So gate, drain, and source, and the N-type and the P-type field effect transistors is presented here. The semiconductor channel where the current flows could be either of P-type or N-type, and this gives rise to the 2 types of the categories of field effect transistors, namely the P-channel and N-channel. Further, we can divide field effect transistors into the categories depending on whether the increasing voltage on the gate is depleting or enhancing the number of the charge carriers available in the channel, thus creating either the enhancement mode FET or the depletion mode FET. Generally, field effect transistors characteristics are very close to those of the bipolar transistors. So they have high efficiency, instant operation switching, they are robust, cheap, and can be used in most electronic circuit applications. As it was mentioned, as only electrical field control the current flowing in the channel, the device is said to be a voltage operator. It has a high input impedance, usually in mega ohms. And this high impedance makes the FETs sensitive to the input voltage signal, which is good but comes with a price that they could be easily damaged by, for example, some static electricity. FET also could be made smaller than a bipolar junction transistor, and along with their low power consumption generally and power dissipation, it makes FETs better for the integrated circuits and an application as a CMOS range of logic chips. One of the most popular field effect transistor is, of course, MOSFET, or the metallic oxide semiconductor field effect transistor. So before making the contacts for the gate terminal, usually a layer of the insulating material like the silicon oxide is grown above the substrate to increase the gate resistance. And to better demonstrate how it's done, let us make a break and watch a nice video.
About FETs, or more specifically, MOSFETs. We've done videos about bipolar junction transistors, or BJTs, and while MOSFETs may also be transistors and share many similar properties superficially, the way they operate is completely different. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. Right now, that may just seem like a bunch of random words mashed together, but once you understand how it works, this name will make perfect sense. MOSFETs still act like switches by varying the voltage on one terminal, the gate. It changes the resistance between the other two terminals, the source and drain. Let's discuss the makeup of your MOSFET using an NMOS in enhancement mode as an example. With an NMOS, you have a P-type substrate that you then create two heavily doped N-type regions. These two regions are called the source and the drain region. With our knowledge of semiconductors, you can see that you're creating a PN junction between the substrate in these two regions. On top of the substrate, an oxide, which acts as an insulator, is deposited. Then on top of that, a layer of metal is deposited, which finalizes the gate structure. Now you can see where the metal oxide semiconductor in MOSFET comes from. But it may seem strange to have your gate being completely electrically isolated from the rest of the circuit. This is where the FET term comes in. Even though there isn't a direct electrical connection, the voltage on the gate creates a field effect. As we know from our studies about diodes, at a PN junction, a depletion region is naturally created even when there are no electric fields. This is the natural state when the gate voltage is 0 and the MOSFET is operating in the cutoff region. This is an operating region, not a physical region, which can be confusing. If you increase the gate voltage, that positive voltage will repel holes in the substrate away from the area between the source and drain, an area called the channel region, this time a physical region. As the free holes leave the channel, only negative fixed ions are left, creating a depletion region across the entire channel. Besides this depletion region, an inversion layer of electrons starts to form at the source, and as the voltage increases, that inversion layer expands toward the drain. However, at this point, when the gate threshold is not yet equal to the threshold voltage, free carriers do not yet connect all the way from the source to the drain. This area of operation is called the saturation or pinch-off region. However, as the gate voltage continues to increase, increasing the electric field, and finally passes the threshold voltage, electrons from the source and drain flow in and form an inversion layer of electrons that connects the source and drain regions. Now that they're connected, if a voltage is applied across the source and drain, a current will flow. The MOSFET is now operating in the linear or triode region. This is how, using a metal oxide semiconductor structure, you can use the field effect of a gate voltage to create a semiconductor switch. And to get a PMOS device, you have an N-type substrate and heavily P-doped wells for your source and drain, and the current carriers are holes instead of electrons. Also, I mentioned earlier that this is an example of an enhancement mode device. It's called an enhancement mode device because an increased gate voltage enhances the conductivity of the channel. Some MOSFETs are designed so that they naturally have a conductive channel, and a negative gate voltage is needed to actively turn it off, and these are called depletion mode devices. Conceptually, that's basically all you need to know to understand the mechanics behind MOSFETs. For the most part, everything stems from these operating principles. But there are a few things that I'd be remiss to not mention that can affect their operation. First is the channel length, L, the distance between the source and drain. Second is the channel width, W, which is how long the source and drain are. These two features are very important when it comes to designing a MOSFET. Third, in this example, we assume that the substrate or base was connected to ground. That's usually the case, but not always. No matter what, you need to make sure that the source and drain are at equal or higher voltage potentials than the substrate, or else you will forward bias that PN junction and get an unwanted current. This topic can be surprisingly confusing, and I personally believe that it's in large part due to the amount of terms, especially those that stand for the same thing, such as linear, triode, and ohmic, to describe the same region. Unfortunately, that's just the reality of the situation, and it will just get easier with experience and familiarity. I hope that this at least gives you a good foundation as you start to use or design MOSFET transistors, so you have an intuitive understanding of how these operate. If you like this video or you found it interesting, please subscribe to our channel and go to circuitbread.com, and we'll catch you in the next one.
I actually highly recommend this channel. It's very interesting, and it gives a lot of good explanation on the electronic devices and the physical phenomena underlying them. So let us switch further to the another advancement in the field of electronics. MOSFET was a go-to design for a long time in the majority of the electronics application of field effect transistors. However, the demand for the better efficiency and smaller sizes pushed the technology, which produced such an interesting device, which is implemented in the industry nowadays, roughly from 2010 to 2014. It's a FinFET, or multi-gate device. We already reviewed how it is compared to the traditional planar transistors and what are advantages and disadvantages. Just a few words. So in a traditional 2D planar transistor, a conductive channel is formed in a silicon region under the gate. So in traditional planar resistance, we don't see this fin. It's just all straight up under the gate when the under the gate electrode when the transistor is in on state. And here it's the 3D three-gate transistor, or the FinFET, and it forms the conduction channel on the three sides of the vertical fin, providing a fully depleted operation. Why it's important? Because it offers a lot of advantages over the planar MOSFET. So from the point of view of a designer, the current voltage curve gets flatter, meaning that we have a lower dynamic power consumption. The fully depleted structure enables better on and off contrast. From the physicist point of view, having this fin, why it's called FinFET, because actually this looks like a fin of the fish. So this fin allows for channel quantization, leads to sharper contrast between on and off states. Again, the channel quantization leads to better current density due to the confined density of states instead of just free density of states as in 2D transistor. And again, channel quantization reduces short channel effects by more effectively separating the source and drain rather than just letting them couple through the NPN or PNP junction beneath. For us as users, while it results in a faster switching speed, comes from lower input capacitance and higher dynamic current density, and lower power consumption. So comes from the low parasitic capacitance and better on and off characteristics. Of course, the difficulties are that it's a new design, it requires further implementation and a change of the manufacturing processes. Further advancements were achieved in the form of the gate-all-around, also known as the surrounding gate transistor concept, which is similar to the FinFET, except that here the gate material surrounds the channel region on all sides, not just on the three sides. It could be realized in the form of the nanowires, whether the lateral or the vertical, or in the form of these nanoplates, nanosheets, as presented in the Samsung MBC FET design. Again, we have already reviewed both videos and these materials, so I'll proceed further. Just very interesting how we can work with this, further pushing the properties of the semiconductor to its limit. Also, it's important to note that nowadays the transistors are not created solely from the silicon, where it usually have the mixture of the germanium. So we have a silicon germanium compound to improve the transport properties. But to go to more sophisticated below 7 and 5 nanometers devices concepts, the manufacturers and the industry start to pay more and more attention to other types of semiconductor. For example, one of the gate-all-around FET concept devices was offered on the basis of this indium gallium arsenide, indium phosphide lattices, where the nanowires were realized from the indium gallium arsenide, so the 3,5 semiconductor. As gallium arsenide and other 3,5 semiconductors could be a solution for the shortcomings of the silicon-based electronics, silicon is still on the top of its game. This group 4 semiconductor is used in all the electronics, in the solar cell applications, light emitting diodes, and high voltage devices. The germanium, from which actually the first transistor was made in 1957 in Bell's lab, is closely following by, specifically as it was mentioned in in the form of compound together with silicon in electronic devices. But also it's used to manufacture rectifiers and transistor weapons sighting system. Gallium arsenide is a 3,5 semiconductor, which is typically found in the integrated circuits working in the microwave frequency range. Also in solar cells, laser diodes, different photodetectors with high electron mobility, etc. And even more niche application could be found for another representative for the 3,5 semiconductor group, for gallium nitride, which we know is found in light emitting diodes, in the power electronics and lasers, or cadmium telluride, which is 2,6 semiconductor and is typically found in solar cells applications. Lately, gallium arsenide gains more and more attention on the wide scale by many manufacturers, by the whales of the electronic industry, like Intel, for example. However, it still is found in many niche applications. I'm not surprised because gallium arsenide, it has some electronic properties that are superior to those of silicon. But before proceeding comparing those two, a few words about its basic parameters. It's a gray crystal with a zinc blende crystal structure, meaning that we have two atoms, gallium and arsenide, forming two interpenetrating FCC face-centered cubic lattices. So the gallium has 3 valence electrons, arsenide has 5 valence electrons. Combining them, we have a 3,5 semiconductor with 8 valence electrons on the outer shell, a stable compound. They blend very well because the gallium and arsenides have similar electron configuration and atomic radius. Also, pay attention at the mobility and the resistivity values for the gallium arsenide, because in comparison to silicon, these parameters are way, way higher. So as you may see, the electron mobility of the gallium arsenide is at least 5 times larger than those of the silicon, while the hole mobility is still lower. Also, a big advantage is that the thermal conductivity is lower than in silicon. What does it mean? So a high electron mobility means that you can shoot electrons across the transistor faster, get a higher gain and higher bandwidth of transistors, get a better conduction with a lower doping level. And lower thermal conductivity means that material conducts less heat. And of course, as a rule of thumb, the lower the thermal conductivity, the better. So the gallium arsenide is 3 times lower than silicon, 3 times better than silicon. Because gallium arsenide devices generate also less noise than silicon devices, gallium arsenide could be used in high frequencies applications up to 250 gigahertz. It's commonly found in Wi-Fi routers, and you may certainly find gallium arsenide at the heart of your cell phone's receiver and transmitter. Another advantage of gallium arsenide is that it has a direct band gap in comparison to the indirect band gap of the silicon, which opens the path to the applications in optics. as well as from the point of electronics, it allows for the direct on-chip generation of light for signaling and detection, which would effectively allow for all optical buses instead of the complicated design of the metal lines. High resistivity, high saturated electron velocity, high electron mobility, and high breakdown voltage are all the advantages for gallium arsenide. So among all these advantages of the gallium arsenide over the silicon, why we are still seeing the gallium arsenide in niche applications while silicon is dominant on the electronics market? You see, gallium arsenide has poor hole mobility, the first thing. When we are looking at the electronics for the CMOS technology in particular, you have N-type and the P-type transistors together that are forming logic gates. The currents through the N and P-type devices have to be balanced in order to have a well-functioning device. Otherwise, you will have jitters, you have time delays. And in order to balance the current, you need somewhat a decent balance of the electron and hole mobilities, because you will need to use the same proportion as between these mobilities on gate widths in order to balance the current. So when in the silicon, we have the situation with the proportion of electron to hole mobility around 2 to 1, 3 to 1, depending also on the manufacturing process and whether any dopants were used. So it means that P devices have to be twice as wide as N devices in the transistors or in the any logic device. It's doable. But when we look at the gallium arsenide, we see quite a large difference between them. So the ratio here, even in the best case, is 10 to 1, 9 to 1. And this will be very big disadvantage in the current CMOS applications. Also, the gallium arsenide doesn't have a natural oxide. You have to perform some chemical vapor deposition to get the oxide or the nitride insulating layer on the top of the gallium arsenide. And even through this complicated process, the achieved oxide will have comparatively to the silicon oxide poor quality, and it won't stick nearly as well, leading to the manufacturing defects. So gallium arsenide is not the best candidate for the MOSFET. Another disadvantage is a high production cost for a small output size of the crystal. Hence, the manufacturing process is times and times more costly in the case of gallium arsenide in comparison to silicon, thus limiting its applications to some niche fields. So gallium arsenide applications are commonly found in the field of electronics, some circuit topologies and devices types, mainly FET logic. Also, despite the shortcomings with MOSFET, the gallium arsenide could be used in a MOSFET, or the metal semiconductor field effect transistor, which is a device where a Schottky or metal semiconductor junction is used instead of the PN junction for a gate. Gallium arsenide is found in defense and aerospace for the radars, secure communication, and sensors. Also, high-frequency technologies are taking advantage of the capabilities of gallium arsenide to work with frequencies over 250 gigahertz. Thus, gallium arsenide is found in a VLAN, in the GPS systems, in the satellites, mobile communication, and so on. Gallium arsenide, as it's rightly mentioned here, allows new digital transmission techniques with a high radio frequency power and lower voltage amplifiers to maximize the operation and standby time. So generally, they can be operated at higher power levels than the equivalent silicon devices because they have a higher breakdown voltages. And the last but not least are the photoelectric cells, the tunneling diode, and lasers. The solar cells and detectors are specifically interesting field for the gallium arsenide and doped gallium arsenide applications because Even in 1980s, the efficiency of the gallium arsenide solar cells was higher than of silicon, and starting from 90s, gallium arsenide took over silicon as a most commonly used solar cell type for the photovoltaic arrays of satellite application. Though the field that requires an efficiency and a good outcome, and it's not so counting money like modern electronics. Additionally, gallium arsenide is a very good base for other 3-5 semiconductors, specifically for the dilute magnetic semiconductors. As this chapter is a part of the Advanced Spintronic Materials lecture, at some time we need to add the magnetism to the equation. Coming back to the question that was asked earlier in the beginning of the lecture 2, what are materials suitable for spintronics? So the ferromagnetic metals were already discussed in the lecture 1, magnetic materials. Well, I would like to cover magnetic semiconductors and dilute magnetic semiconductors. So let us start with a magnetic semiconductor. Some 60-70 years ago, the magnetism was more a domain of metals, as a ferromagnetic long-range order is present in these materials. And it was quite a surprise to discover in some materials like europium chalcogenide or the chromium spinels the ferromagnetism. These materials are insulator and they showed antiferromagnetic or ferromagnetic spin ordering, which is driven by the superexchange interaction. Sometimes the superexchange can lead to ferromagnetic short-range coupling between the localized spins, like in cadmium chromium selenide, and gives quite a high Curie temperature, which is Saint Graal for all the magnetic and dilute magnetic semiconductor technology parameter. Curie temperature means that we have a paramagnetic state above it and a magnetic state below it. The typical room temperature is 300 Kelvin, and obviously for a material to be considered for the applications, for real life applications, the TCE needs to be at least 300-320 Kelvins, which is not, unfortunately, the case of many materials that will be mentioned now, but that is why we are working in physics, to overcome these obstacles. So coming back to our chalcogenides in europium oxide, the antiferromagnetic superexchange is overcompensated by the direct FD ferromagnetic exchange that gives in comparison quite high Curie temperatures like 70 kelvins, which could be achieved in the liquid nitride. And after this discovery, magnetic semiconductors were investigated more intensively, and a lot of interesting effects like colossal magnetic resistance, magneto-optical effects were discovered and rightly assigned to the exchange interaction of the band carriers and the localized spins. So what are the applications of these rather exotic materials? For example, most of the materials are antiferromagnets. They could be good candidates for the antiferromagnetic spintronics, a new emerged field which takes actually advantage of something that was considered a shortcoming for a long time. As an antiferromagnet, we have two magnetic sublattices that are compensating each other below the transition temperature. Thus, we have the zero magnetization below this nil or transition temperature. For the magnetic application, it could be a disadvantage. However, now we know that it could add additional degree of freedom, which we could implement in the antiferromagnetic spintronic devices. Also, it was discovered that some of the magnetic semiconductors are van der Waals materials. So these are layered materials composed of planes that are attached to each other via the rather weak van der Waals forces, like the graphene or molybdenum. And in combination with other 2D materials, they can create new materials, that possess a wide variety of attractive properties. And finally, we arrive to the dilute magnetic semiconductors. This material family was initially named semi-magnetic semiconductor, as it consists of, as you may see on this panel, the host non-magnetic semiconductor, gallium arsenide, could be, for example, indium phosphide, doped with magnetic impurity, which is usually a transition metal atom. Could be manganese, could be cobalt, European, and so on. So the typical representatives of the dilute magnetic semiconductors are cadmium manganese telluride, zinc cobalt oxide, plumbum European sulfide. He has a short-range antiferromagnetic superexchange between the manganese and heavier 3D transition metal ions like cobalt, or long-range dipolar interactions between the rare earth magnetic moments could lead to quite an exotic states of matter like spin glass freezing. Not only this, but generally binary compounds like manganese selenide or European telluride are insulating antiferromagnets and attract attention from the point of view of, again, antiferromagnetic spintronics. Dilute magnetic semiconductors could be used in a qubit system consisting of a single magnetic ion in a single quantum dot. All the transport and optical properties of these materials are very sensitive to magnetic field because of the SPD exchange interaction that leads to large band splitting. SPD is just the hybridization of host sp states and the d states, d orbital states from the transition metal ion. Strong spin-dependent coupling typically leads to the antiferromagnet superexchange, similarly to the magnetic semiconductors as were discussed earlier. However, for the systems with a high density of delocalized or weakly localized holes, like in a p-type dilute ferromagnetic semiconductors, these could actually lead to long-range ferromagnetic interactions between transition metal ions, and this could override this anti-ferromagnetic superexchange. This is all very well described by Mu universal RKK-Y model or the PD Zener model specifically for the dilute magnetic semiconductors. The flagship of this p-type dilute ferromagnetic semiconductors is gallium manganese arsenide. So we have the gallium arsenide, which we nicely described beforehand. We add a manganese. Manganese is a typical transition metal ion in all of these class of the dilute magnetic semiconductors. And in the end, we obtain a nice DMS with a Curie temperature as high as 200 kelvins. So let us discuss these dilute magnetic semiconductor subclasses a little bit one by one. Let us start with 2,6. The 2,6 is a very interesting class where you can have different properties depending on a smart choice of the semiconductor material and the transition metal ion. So the semiconductor host material itself varies from the insulator to narrow forbidden band material to semi-metal. And transition metal could be manganese or cobalt or ferrum. Usually the manganese-based, the most intensively and widely studied, not only for the 2,6, but generally for 3,5 and 4,6 as well, because they allow for quite a nice composition range and produce the best materials in the end. Also, by playing with this composition of host semiconductor transition metal ions, we could have wide gap and a narrow gap materials. It's easy to prepare, but still, even in comparison to other semiconductors, dilute magnetic semiconductors, it's hard to dope. It was shown in the literature it's hard to find a single crystal that will incorporate the transition metal in a whole composition range, so from 0 to 1. Still, it's better than 3,5 or 4,6. However, it limits its possible application. Typically, they are grown by the Bridgman methods and its modifications. As for the applications, the oxide to 6 group semiconductors are the preferred compounds in the Spintronic devices application because of their interesting properties. Some 2,6 with the manganese are characterized by high electroluminescence that makes them important for the optical flat panel display applications. And the dominant interactions here are the antiferromagnetic, so the localized magnetic moments talk to each other via the antiferromagnetic exchange. This, together with the randomness of this magnetic ion distribution, results in a disorder spin orientation in the absence of external magnetic field, even in the lowest achievable temperatures. So it could be a point material of interest for the antiferromagnetic spintronics solemnly. Compared to the magnetic semiconductors that were investigated earlier, shown on the previous slides, the 2,6, for example, exhibit smaller concentrations and are easier to dope with shallow impurities. Many phenomena that are interesting to investigate in the 2,6 are the giant Faraday rotation, the magnetic field-induced metal insulator transition, the formation of the bound magnetic polarons. So more a physical phenomena, more a playground for the physical phenomena investigation. Manganese in 2,6 as the most widely investigated representative of this subclass is electrically neutral. So in order to have for material to be conductive, we need additional doping by acceptors. The typical direct band gap in the case of the manganese doping is located at the gamma point for the Brillouin zone. And here the short range again, antiferromagnetic superexchange determines, depending on the concentration of manganese, whether we have the paramagnetic states for the low concentration, whether we have spin glass state for the higher concentration. And also ferromagnetism for the p-type was observed, which is quite interesting. In conclusion, from the practical point of view, many gross complications and rather exotic materials for mass production like mercury, well, actually some mercury materials show nice properties, but to have a strong infrared optoelectronic device with a toxic mercury is still not desirable for the practical application. So all these creates obstacles for the mass productions, together with the high cost of the production of this material. But it's interesting from the point of view of the spin phenomena investigations, like antiferromagnetic, paramagnetic, and spin glass behavior. And now we arrive to another interesting material from the point of view of carrier-mediated ferromagnetism. These are alloys of the group 4,6. They have typical rock salt structure, representatives being plumbum manganese selenide, plumbum manganese and telluride. And similarly, a fraction of a host material here is replaced by the transition metal ion, manganese, europium, or gadolinium, for example. But in this case, magnetic ions have, as you may notice, partially filled 3D and 4 or 4F shells. The typical growth methods are the Bridgman, and with this we can produce both P and N type structures like plumbum manganese telluride that have both direct and indirect band gaps. So it's interesting for the investigations. But still, the composition range in which we could introduce transition metal ion is very low, and the obtained results are not so prominent in comparison to another class that we're gonna discuss now, the 3,5. For quite a long time, 3,5 dilute magnetic semiconductors, a fine representative being gallium manganese arsenide and indium manganese arsenide, they suffered the same fate as their colleagues and cousins from other subfamilies. So low solubility of transition metals, grown by the, in this case, molecular beam epitaxy in contrast to Bridgman method. So this was a plug putting ideas of the concept devices on the shelf. However, specifically for this material, in the late 90s, it was partially solved by the reduction of gross temperature from 400-600 Celsius to 220-240 Celsius. And only this allowed to introduce more dopant in the host Zener lattice structure. In the case of gallium manganese arsenide, it was possible to substitute up to 20% of the gallium size with the manganese. Even with this, comparatively low values, especially low in comparison to the 6, the Curie temperature observed in the end was very high. It was 191 kelvins for the layers and 200 kelvins for the patterns structure. Main characteristic properties of the 3,5 dilute magnetic semiconductors are zinc blende lattice structure of the host semiconductor. The typical go-to growth methods are the molecular beam epitaxy and low temperature molecular beam epitaxy that allow to have better quality in comparison to even Bridgman method. The main doping is manganese, as these ions act as acceptors, supplying both host and localized spins. So we are making our material magnetic and creating an p-type material at the same time. Manganese ion is then 2+ with a spin 5 seconds, which leaves us with a weakly bound hole. Despite, as it was mentioned, the quite a low solubility of manganese, still 20% is not high value, but the achieved Curie temperatures are quite high, and maybe a new breakthrough will come, so we will make a jump up to another 100 kelvins to achieve the room temperature. Both P and N-type dilute magnetic semiconductors could be created. The highest carrier concentration, though, was observed for the P-type gallium manganese arsenide, up to 10 to 21. The magnetism is a hole controlled in the most of the 3,5 dilute magnetic semiconductors, and general mechanism between this is well described by the RKKY model, or more specifically for the dilute magnetic semiconductor, PD Zener model. There is a wide variety of methods with which we could manipulate the magnetization of these materials that makes it so attractive for the practical application, with a light, with a strain, with a field. The phenomena observed, those are also of special interest for the spintronics, like giant magnetic resistance, tunneling magnetic resistance, various kinds of Hall effect, and spin injectors were possible to create on the basis of these 3,5 dilute magnetic semiconductors. And one of the most prominent features, of course, from the practical point of view, is that it's based on the gallium arsenide, which we well described several slides earlier. So it's well compatible with the existing semiconductor technologies, and it does require a large jumps and changes of manufacturing processes. And we can step-by-step work with this dilute magnetic semiconductor in tandem with just a regular semiconductor. We also can exhibit different states of the material dependent on the concentration of the transition metal ion. So in a case of, again, gallium manganese arsenide, if the less than 1% of manganese was introduced into the host Zener blende lattice, we see the insulating to paramagnetic phase. Distance between the holes bound to the manganese ions is much larger than the size of the bound hole. It leads to this insulating to paramagnetic phase. Then the medium concentration of mangan, here is being around 1%, leads to insulated to metal phase, and the overlap between the impurity and band and the valence band start to develop. And with a higher concentration of manganese, it becomes ferromagnetic. So at low temperature, of course, because the impurities are closer and long-range Coulomb potentials are screened, it leads to imperfect metal like state of the imperfect metal with disordered broadened and shifted bands. Impurity and host band are now completely merged together into one inseparable band, which may has this localized state depending on the concentration of the carriers, which is well shown here on this slide. So the low concentration, we have a separate bands, the manganese impurity D band and SP band of the host semiconductor. Then with the increase of the concentration, we are arriving at the start of the hybridization between the bands. And in the end, the metallic conduction takes place when there is a nice and full hybridization of these bands. Describing in more detail the exchange interactions that takes place, of course, we already mentioned the PD hybridization that results in a spin-dependent interaction or kinetic exchange. And because this SPD exchange interactions, the electrons and the SP bands are attracted or repulsed by the given magnetic ion depending on their spin orientation. That results in a special separation in spin down and spin up electrons if the bands are entirely occupied, as an insulator or intrinsic semiconductor, which in the beginning leads to antiferromagnetic exchange between neighboring localized spins, superexchange, and spin splitting bands is proportional to the magnetization M of the localized magnetic moments. Strong spin-dependent interaction between the electrons in the SP band and those on the D shell of impurity that are they are described by the exchange coupling, more precisely by the Heisenberg exchange coupling. Then a model could be applied without adjusting any parameters in cases of gallium manganese arsenide, for example, as electrically charged. Here we have charged again manganese pairs are ferromagnetically aligned by the holes, while RKKY corrections to this Zener model are required in a case of, for example, zinc manganese telluride, which spins are electrically neutral. So nearest neighbors have electrically neutral spins and they remain in this anti-parallel configuration. Magnetization, as it's mentioned here, is proportional, like spin splitting bands is proportional to the magnetization M of the localized magnetic moments. Magnetization is also dependent on the dimensionality. So within the Zener model, Curie temperature, the main parameter of our magnetism, is proportional to both manganese ion concentration and density of states for spin excitation. So this density of states increases with the whole concentration in a case we have a 3D system, but stays constant in the 2D systems. For n-type manganese-based dilute magnetic semiconductors, a carrier-induced ferromagnetism is also observed under some rather restricted conditions due to a relatively small magnitude of the SD exchange coupling and this density of state. An interesting material of this 3-5 class is a gallium manganese nitride. It can exhibit ferromagnetic properties up to the room temperature and involve up to 20% of the manganese spins. But origins of this magnetic response is still an open topic. A general comparison of the different Curie temperatures in manganese-based ferromagnets is given here. These are the theoretically calculated Curie temperatures for the fixed amount of mangan being 5%, and these are p-type materials with a concentration of hole being 3.5 times 10 to 20. So the gallium nitride is definitely leading the way, but practically it was shown that we can achieve this, but practically achieve this with a good degree of repeatability was still quite a challenge in this field. And now we arrive to the champion from the dilute magnetic semiconductor side, to the gallium manganese arsenide. As it was rightfully named, it's one of the most studied spintronic materials. It's a good model not only from the applications point of view, because it has a high TC, it could be easily tuned, for example, by doping, by strain modulation, but it also caught our interest as a playground for the physical phenomena investigations. So this 3,5 dilute magnetic semiconductor is a p-type. Again, the transition metal ions used here are manganese. They are manganese 2 plus from the half-filled 3D shell. The band gap for a typical manganese concentration for 6% is 1.43 electron volts. And the ferromagnetism, like ferromagnetic ordering of relatively widely spaced manganese dopants, arises from the antiferromagnetic interaction between the manganese 3D magnetic moments and delocalized charge carriers. In other words, we can say that we have a carrier-mediated magnetism. And already a lot of interesting devices, concept devices, of course, were made on the basis of the gallium manganese arsenide and other 3,5 materials like aluminum gallium arsenide and gallium manganese nitride. A lot of effort was put into the gallium manganese arsenide, and here you may see just a few of the keystone investigations, like the milestones of the gallium manganese arsenide description. Generally, after the enhancement of the molecular beam epitaxy, lowering of the temperature, a very intensive investigation from the scientific community started, like the Curie temperature manipulation described in the work of Professor Hideo Ono, or the gettable ferromagnetism, an interesting physical phenomena that lie behind the domain wall mechanics were described by Professor Fukumura just merely 19 years ago. The spin transport was also described in the concept of the vertical spin transport of manganese arsenide, gallium manganese arsenide heterostructures. The very nice overview, if you are interested in a general application of this material in spintronics, was given by Good et al. In his work in Advanced Materials, which I highly recommend. To understand what forces and what interactions are at play, let us look at the perturbation of the crystal potential with doping. So if we will introduce to our gallium arsenide, this is a valence band. So if we will introduce a single manganese impurity, then we will observe three key components that will perturb our potential. First, it's a long-range Coulomb potential. It's of a single acceptor in gallium arsenide. So this is our single acceptor, and it creates a bound state at about 30 millielectron volts above the valence band of the host semiconductor. The second contribution is a short-range central cell potential, which is specific to a given impurity. And it reflects this difference in the electronegativity of the impurity and the host atom. Because of the kinetic SPD exchange and the central cell interactions, these manganese acceptors are more localized than the shallow acceptors. So the shift of the P level is 1.5 electron volts, which implies that central cell's contribution to the acceptor level of this manganese that substitutes gallium single impurity is around 30 millielectron volts. And the remaining part of our contributions of our components is the binding energy due to the spin-dependent hybridization of the gain manganese D states with neighboring arsenide P states. This could also be visualized through the energy model, as again it was shown earlier in the low temperature grown gallium arsenide. Here the split valence band to the heavy and light host levels. So there is no impurity band, obviously. With a low concentration, we see just a beginning of formation of the impurity level. And with a high enough concentration of the manganese, there is hybridization, this SPD hybridization, corresponding to a nice metallic regime. So we have delocalized holes with a low temperature density, and manganese density is 2 orders of magnitude large in this case, and gallium arsenide shallow acceptors. So the long-range Coulomb potentials are screened, and we are arriving at the imperfect metal with disorder broadened and shifted bands. So, of course, in order to understand the magnetization in depth, one may need to dive deeper into sophisticated and complicated physical models, starting with a mean-field Zener model. Without giving too much information, I would just to highlight that within this Zener model, spin magnetization is a function of temperature, and the magnetic field is determined by minimizing the free energy. With this model, we can describe the magnitude of the saturation magnetization and hence give us the overview of the Curie temperature. We can describe physical phenomena like magnetic anisotropy, magnetic stiffness, and etc. Also, because of the ratio of the valence band exchange splitting to the Fermi energy and the magnitude of the spontaneous magnetization, which depends on the temperature, they determine a degree of the occupation of the particular hole subband, heavy hole or light hole. We have the strain-induced anisotropy. In addition to strain, so maybe we have compressively strained layers, we see the in-plane magnetization. If we have tensile strain layers, we see the out-of-plane magnetization. In addition to strain, anisotropy can be manipulated by temperatures in samples with appropriately low hole densities. Large magnitude of a spin stiffness, also interesting parameter in gallium arsenide. It results in a lost energies of both domain walls and spin wave excitation, which could be of interest for some micromagnetic properties. And generally, if you calculate the hole concentration in your gallium manganese arsenide sample, so with some assumption and approximations, you can calculate the expected Curie temperature to be somewhere as, okay, we have the interception of the Curie concentration and the KP Luttinger model, which is shown by the solid line. So if you have 10 to 20 concentration of holes in your gallium manganese arsenide, you should expect around 50 kelvins. Look for the TC around 50 kelvins. So, as we understood, the manipulation of magnetization could be done via various means, and one of the most easiest achievable for at least this type of materials is manipulation with strain. The crystalline anisotropy depends on the growth directions in such a way that if we grow gallium manganese arsenide on top of gallium arsenide, for example, we are forcing the gallium manganese arsenide with lattice parameters larger than of layer below. So we are forcing this gallium manganese arsenide to fit to the layer of gallium arsenide. Thus, we are introducing a compressive biaxial strain, and we are observing an in-plane magnetization with an easy axis along 100. It's a cubic anisotropy, and additional contribution arises between non-equal contributions via 100 and minus 110, which is uniaxial anisotropy. As you may see here nicely on the picture, it's visualized in the form of the magnetostatic free surface energy, which is derived from the magnetotransport measurements under various directions of applied magnetic fields in low temperature in helium. The deepest energy minima corresponds exactly to the easy magnetization axis. And in a case, if you grow your sample, your gallium manganese arsenide on top of a layer that has a larger lattice perimeter, then we are stretching our gallium manganese arsenide, and in such a way that we have only one easy magnetization direction along 001. Hence, we have out-of-plane magnetization. In addition to the crystalline anisotropy, we can play with a shape-dependent anisotropy, which means that by a proper patterning and proper lithography and etching, we are creating such a narrow stripes of the material, as indicated here by Golden, on the top of the, for example, the substrate. It's usually done in a case of the in-plane magnetization or compressively strained case. So we are creating a pattern-induced magnetic anisotropy caused by the misfit relaxation, which take place perpendicular to the lithography pattern nanowires. And in this way, the spins of the magnetic ions are aligned along, so they're pointing like this way. Now they are aligned along the wires. Hence, introducing additional degree of freedom then can be used in some spintronic operational devices. So, as I already mentioned earlier, when describing 3-5 dilute magnetic semiconductors, a go-to method to create the layers is molecular beam epitaxy. And in the case of the gallium manganese arsenide, it's a low temperature molecular beam epitaxy. This technique could be described as a refined form of the vacuum evaporation or physical vapor deposition. Here, in contrast, we have a precise control over the material purity, over the interface formations, over the composition and doping concentration. So we even can have very sophisticated structures like superlattices and heterostructures growing within this technique. But this high crystallographic quality comes with a price. This price is a low growth rate and a very high price of the equipment, high, let us say, period of getting involved and mastering all the parameters for the growth procedure. Sometimes the physicists that worked with this equipment call it most broken equipment, not molecular beam epitaxy, because of how often it can get broken. And this could stop your measurements for quite a long time. Coming back to physics, the major feature that actually enables these qualities is extremely high. It's UHV chamber. UHV it stands for ultra high vacuum. So this environment is very important for the material growth. During the molecular beam epitaxy, non-interacting molecular beams of the materials that we want to have in the end of these constituent materials, they are evaporated. And then they are allowed to evaporated from the diffusion cells, and then they are allowed to chemically interact on a heated substrate, which is positioned here. The beams do not interact in the gas phase because they possess a mean-free path much longer than the typical, usually 20 to 30 centimeters source to substrate distance due to the ultra-high vacuum conditions. Molecular beam epitaxy is very nice for producing sharp interfaces. The diffusion cells, they produce a MBE of the source materials, typically paired with a mechanical shutter that can quickly open and close. And thus we can manipulate with a very precise up to the atomic layer deposition of the material. The temperature of the source, which is very reproducible and stable, controls the flux generated from the fusion cells. This makes the generation of these fluxes of materials in theory relatively easy to control to accurately have composition of the alloy or compound in the end result. The presence of this ultra-high vacuum also allows for the incorporation of various in situ methods like the read or reflection high energy electron diffraction, or LEAD, low energy electron diffraction, also mass spectroscopy. And when combined with non-UHV specific techniques like epsilometry, pyrometry, band edge thermometry, this MBE epitaxy becomes a very powerful tool to study basic science and the production of high quality materials. In the case of gallium manganese arsenide, we are growing the material via the low temperature molecular beam epitaxy. And this reduction of temperature is connected with the fact that gallium manganese arsenide is a non-equilibrium material. So in higher temperature, large flux of manganese caused segregation and formation of the complexes of manganese arsenide, which prevented for higher Hall's concentration. And now we have a relatively high Curie temperature, nice magnetization properties, high Hall concentration. And it was investigated by many groups, including my previous group from the Institute of Physics Polish Academy of Sciences. We have worked with gallium manganese arsenide with 6% of manganese. We have subjected it to various characterization techniques, structural characterization techniques. Of course, it includes read diffraction during the cross procedure. So all the high resolution X-ray diffraction, the TAM and SAM images, and the SIMS plots, they all confirmed the very nice and high quality state of the gallium manganese arsenide that we are now able to grow. Now we arrive at a final part where we would try to combine what we have learned in the first part of the lecture, namely different concept devices, different devices in electronics and concept devices in spintronics, and how they are combined with semiconductors and dilute magnetic semiconductors. One of the most interesting and advanced application of spintronics is a spin polarized field effect transistor. It's a interesting concept, however, it's not still realized, but it's awaiting its time, and a lot of manufacturers are contributing to the development of this technology. So how it looks? Spin-FET is composed of the two ferromagnetic contacts, source and drain, which are sandwiched by the semiconductor region. The ferromagnetic contact contain mostly spin-polarized electrons, and they play a role of a polarizer and analyzer as first described by Data and Das in their impressive work. So the ferromagnetic source contact injects spin-polarized electrons into the semiconductor region. And because of the non-zero spin-orbit interaction, the electron spin processes during the propagation through the channel. So at the drain contact, only the electron with the spin aligned to the drain magnetization can easily leave channel and generally contribute to the current. Thus, total current through the devices depends on the relative angle between the magnetization direction of the drain contact and the electron spin polarization at the end of the semiconductor channel. Current modulation is achieved by tuning the strength of the spin-orbit coupling in the semiconductor region and the degree of the spin precession. Important that the strength of the spin-orbit interaction in the channel depends on the effective electric field, and of course, as we may see here, could be controlled by the voltage applied to the gate. This spin-FET transistor, as envisioned by Data and Das, is a gateway to spin information processing, to the coherent manipulation of electron spins in semiconductors. And I think that realization of spin-FET for information processing, well, it yet to be achieved, but I think it's a fundamental challenge on which we all should work. Of course, on the road to realization of this concept, there are a lot of obstacles, and conductivity mismatch is one of them. So there were a lot of ideas and concepts how to overcome this limitation, among them different materials usage, different combination of materials, different schemes. And here I would like to show you all electric, all semiconductor spin-FET, in which the issue is overcome by using two quantum point contacts as a spin injector and spin detector. So the complete control of the electron spins over the spin injection, manipulation, and detection here is done in purely electrical manner. This device, just spoiler alert, is compatible with a large-scale integration, and I think it holds a promise for Spintronic devices for information processing. The basic material here is indium gallium arsenide heterostructure. It's one of the strong actually contenders also to replace silicon, at least in the part of the devices of the large-scale integrated circuits, and it is used to provide the two-dimensional electron gas channel for the ballistic electron transport and the metallic gate in between two QPCs. QPC are quantum point contacts again. So the QPCs are narrow, as you may see here, short one-dimensional constrictions that are usually formed by applying voltages to split gates. They are patterned on the surface of the semiconductor, and they generate completely spin polarized current due to spin-orbit coupling and or electron-electron interaction. By modifying the gate voltage here, one can control the spin orientation again of electrons traveling along this channel, and gives rise to like oscillation on and off switching of this device with respect to applied gate voltage. So this issue with conductivity mismatch was tackled from the different sides. Of course, the why it's so intensively investigated, well, the efficiency of the spin injection in the original design was less than 1% at the contact area between the ferromagnet and the semiconductor because of the large difference in conductivity. The spin injection could be successful only if the conductivities of the ferromagnet and material are matched and the contact is 100% polarized. Well, so far it was very hard to achieve. On the previous slide, I show you one of the ways to tackle one of these problems. Also, smart material choice, like, for example, if we will have a Hössler alloy as a spin source and semi-metallic Hössler alloy as a transmitting layer, also the problem of conductivity mismatch will be, if not solved, then well, it will be decreased a lot. Alternatively, conductivity mismatch could be circumvented if the interface resistance dominates, as it was shown on the example of the tailored Schottky tunnel barrier approach. One of the most remarkable works on electrical detection of spin transport in ferromagnetic semiconductor was done by Cowell et al. In 2007. So they demonstrated a fully electrical scheme for achieving spin injection, achieving spin transport and detection in gallium arsenide-based device. Device consisted of the main semiconductor channel with several ferromagnetic contacts, sources, and drain to measure both local, when the same contacts are used as a voltage application and detection, and non-local configurations when different contacts are used. So we are measuring spin polarization of the electrons. And in this configuration, we have obviously Schottky tunnel barrier, which electrochemical potential depends on the magnetization, better to say relative magnetization of the sources and drain. And the output signal in this way varies with injection current and is correlated with the spin polarization in the channel. An interesting approach toward the improvement of already existing electronics devices, like a MOSFET, is presented on this slide. So a vertical spin metal oxide semiconductor field effect transistor, spin-MOSFET in short, was proposed on the base of the three layers consisting of gallium manganese arsenide, gallium arsenide, and gallium manganese arsenide, whereas the middle gallium arsenide is a non-magnetic, it's a channel layer, So the source and drain electrodes are ferromagnetic materials, but that are key component for realizing non-volatile application. Such a design allows for high amplification capability, which is advantageous for the large-scale integrated circuits. And of course, the compatibility with already existing base of semiconductors. The main parameters to modulate here are the large magnetic resistance and the large current modulation by applied gate electric field. In particular, this design in a vertical spin-FET, the current flows perpendicular to the field plane and is controlled by the gate voltage applied from the side surface of the channel. So it could solve one of the challenges as it allows for quite a large magnetic resistance. Also, interesting results were observed that this device shows a TMR ratio up to 7%, which is way better than of any planar type spin MOSFETs, indicating that the drain source current can be controlled by the magnetization configuration. Another interesting device concepts that include dilute magnetic semiconductors and gallium manganese arsenide in particular are the EDLT or the vertical spin electric double layer transistors that takes advantage of the fact that Curie temperature and magnetic anisotropy of the ferromagnetics in film could be modulated by a gate electric field applied to the top surface of the film. So this concept presented on the left, successful modulation of the magnetic anisotropy was achieved by applying an electric field. Finally, as we already described the magnetic random access memory, I would like to add that even here, dilute magnetic semiconductors found their way in a form, for example, gallium manganese nitride, the magnetic semiconductor that can store spin orientation even at room temperature, or in the form of gallium manganese arsenide, where, for example, a more sophisticated design that took advantage over the interplay of this crystalline anisotropy and shape-dependent anisotropy in, for example, nano crosses or nano rings can lead to the difference in resistance along different pair of channels, thus creating an states of high resistance, low resistance, or zero and ones, and a possibility to write and record and read information in such a way. And the last slides are dedicated to the literature. Of course, in all my investigations, base for the theoretical phenomena was taken from the Fundamentals and Application of Magnetic Materials by Kannan Krishna, and all the others are presented here. And here. So, gradually, we arrive to the end of our lecture course. With my last words, I would like to express gratitude to all people who contributed and helped this course to be created. Namely, first and foremost, I would like to underline Professor Andrei Chumak, as he was with you from the very beginning, from the introduction lectures. Then he helped to explain the phenomena that are governing the behavior of the magnetic advanced materials and presented you interesting device concepts that are already applied in the electronics and the potential devices basis for the future for the spintronics. Invisible but so important help was done by Dr. Vitaly Yunko and Pedro Daleria Laverne. They are our technical support, and the fact that you see this video is their achievement. Of course, this won't be possible without your view, and I hope you have had as much fun with these lectures as we did. Hope to see you next year. Bye-bye.